This is the virtual presentation for the International Conference on the Constructed Environment held in October 2011 at the University Center, Chicago, USA. The presentation stream is Environmental Impacts and the work is research focused. The title of the presentation is Impact of Climate Change on the Constructed Luminous Environment and Evaluation for the Hospitals in London. I am Ashikur Rahman Jordar and my co-author is Professor Andrew Price. We are from the Health and Care Infrastructure Research and Innovation Center, School of Civil and Building Engineering, Loughborough University, United Kingdom. Climate change has the potential to cause change in sunshine, deplete of ozone sphere, decrease of cloud cover, and reduction of green. As a result, changes in incident, direct, diffuse, and global radiations are expected. As an influence of the changes of radiation values, changes in outdoor ambient lighting levels as well as indoor daylight levels are expected. The objective of this research is to identify the impact of climate change on indoor daylight level. This presentation consists of two major parts. The first part describes the detailed steps of the research methodology to identify the impact of climate change on indoor daylight level, and the second part presents the research findings with conclusion. This is the structure of the research methodology, which consists of 6 steps. The first 3 steps are concerned about the selection of the climate database, geographical location, and 3-dimensional space to be used for simulation study. Next 3 steps are concerned about evaluation measuring criteria, tools, and parameter of simulation study to conceptualize the impact of climate change on indoor daylight level. So let's start with the selection of the future climate change database to be used for simulation study. For building simulation analysis, time series or time scales data are required in hourly or more precise levels. CIBSE 2008 database, modeled by Chartered Institution of Building Service Engineering UK, which supports the projection of climate change described by United Kingdom Climate Impacts Programme 2002, was used as climate database for this research. Next, the location. CIBSE data were produced at a spatial resolution of 50 km and available for 14 UK sites. The current and future CIBSE hourly weather data sets for London are based on the geographical location of Heathrow, which is located at 12 nautical miles west of central London. The 3D inpatient single bedroom used in the simulation exercise as case space was developed according to the guideline described in Health Building Note 0401/2008, published by the Department of Health UK. The case room has 2 windows on the south facade. The first one is a standard viewing window and the second one is a 45-degree angled window placed above the viewing window, which was specially developed for the hospital inpatient rooms that perform better to achieve therapeutic daylight for patients compared to traditional typical high window configurations. The design of the shadings of the windows was as shown in this room section. The windows were considered without any blinds during simulation analysis to isolate the actual impact of the change of outdoor daylight level on indoor daylight level due to climate change, and also to avoid the effect of the operations of the internal blinds in daylighting the space. As higher intensity of daylight needs to be incident on patient's retina to start biological stimulation inside body, The height of the test plane was fixed to 1150 mm above floor level, which represents the patient's average eye level when laying on a bed in different ergonomic positions. For the purpose of the simulation, the entire room space was divided into 500 into 500 mm grids. Calculation of hourly illumination at these 63 intersecting grid points was done for the whole year. Each point has 8,760 illumination data considering 24 hours of the day and 4,380 data considering 12 hours of the daylight from 6 a.m. to 6 p.m. The hourly illumination for individual 63 points were averaged for the whole year at the beginning, and then average of 63 points were taken as the average illumination of the room for one specific time slice under particular emission scenario. The 3D CAD drawings generated in ADB software for single-bed inpatient unit with furniture layouts was imported to Ecotech. Ecotech was used as a modeling interface to launch DAYSIM program. DAYSIM, that used dynamic climate-based daylighting modeling method, was used to generate annual illumination profile for the case space based on current and future test reference years and design summer years hourly weather data sets. To understand the magnitude of the changes in indoor daylight levels, the performance of this case space was compared under current climate with the performance under future climate change time slice, that is 2020s, 50s and 80s, under different level of anthropogenic carbon dioxide emission scenario, for example low, medium high and high, keeping all other features of the case space unchanged. The simulation time step was fixed to 1 hour. This graph summarizes the changes of average indoor illumination level from present to extreme future, considering the average of 24 hours and selected 12 hours of daylighting. It is evident from the graph that increase of illumination levels were higher for design summer years. Based on design summer years, the average illumination level increased 1% from 1989 to 2020s, and the average illumination level increased 2% per 30 years from 2020s to 2080s under high emission scenario. As a result, the average indoor illumination can raise maximum 5% in future compared to present. Comparison of yearly and monthly illumination profile shows that the variation between present and future illumination were not constant. A closer observation of 24 hours daily illumination profile revealed that the average difference between future to present could vary from minus 595 lux to 579 lux in a particular date. To summarize, the evaluation of the daylighting performance of the case space under different future emission scenario revealed that there is a possibility to increase the average indoor room illumination by maximum 5% in future compared to present, with a difference from minus 595 lux to 579 lux in a particular date. It is important to consider how this large amount of variation will be incorporated in the design of daylighting in future. Climate change thus introduces several new issues to the knowledge gaps in daylighting research. In this research, prospective simulation study was done to conceptualize the impact of climate change on indoor daylight levels by evaluating the performance of an imaginary standard hospital inpatient room defined by NHS UK under different future emission scenario described by UK CIPO2. The specific limitations of the climate change simulation study of this research is that UKCIPO2 scenarios are not designed to formally or quantitatively reflect all of the uncertainties of future climate, and the future global and diffuse irradiance data from UKCIPO2 have been generated from synoptic data, mainly sunshine duration and cloud cover, which computer models. Due to the difficulty to obtaining consistent irradiation data. Therefore, the assumptions based on the climate change simulation study of this presentation will only satisfy the projections described by UKCIPO2 and will not support other climate change models, for example, UKCPO9. It is expected that the outcome of this research will help architects and designers to conceptualize the performance of present constructed luminous environment under future climate change scenarios. Thank you. For any question, please contact me at ashikj2000@yahoo.com.